Hello everyone, and welcome to another Jura video. And in this one, despite what I said last time, I think I'm going to implement functions, because this follows on nicely from the last episode, where we added variables, which then meant that we had to add scopes, because functions are just kind of like another thing we're going to be putting in the scope, and we already kind of have function calls. Well, we don't, but we have print, like we can say print 10, and then that'll print 10. I need to have a better way of actually like saying which one we're going to run, but this works for now. And then this is going to take ages to run because it's the first time I'm running this today. So grab yourself a snack, grab yourself a coffee. Okay, while this runs, I'm going to say about what I want functions to be like in Jura, because we already have variables that are assigned like this. So I think functions are going to have a similar sort of syntax. Like I'm going to say they are fun, because that's just the easiest keyword to use. And it's really easy to parse, because if you have like in Java like the type and then the name, you kind of, I mean, it's kind of obvious from where in the context you are defining the function, but having a keyword means that you can reuse the keyword for like lambdas and things like that, or like function type signatures. Like something Java has that I really hate is like a different interface for different signatures of functional interfaces. Like you have consumer for something that takes in a value and returns nothing. You have by consumer for something that takes two values and returns nothing. You have by function for something that takes two values and returns something. You have to have a different interface for each kind of signature, or like each arity of the signature. Whereas if you have just like something a bit more generic, like you could have a type that is like fun int, and that would be like a by function of int to int. But you know, you could just keep going, right? And then I don't even know if Java has a try function. Let's have a look. Well, good old Apache Commons has an IO try function. So yeah, it gets kind of ridiculous, especially if you want some more like complicated functions. Anyway, all that's to say is I'm going to go with a fun keyword, and then the name, and then the inputs are going to be defined the same way that variables are, like this. And then for the return, it would be easy to do something like this, and then you're using a different character or a different token. But to me, like, this makes sense, right? This is the... Well, like, if you say x int, right? Whenever you're saying x, you're putting an int back onto the stack or whatever. Maybe I'm a bit stack-brained at the moment from do. But the output of this character is an int, which is shown by this. So when you do this, oops, typing one-handed with my coffee in my hand, 1 second. You know, when you type this, you're putting an int on the back on the stack or whatever. So I think that the syntax should be the same. It should just be :int. And this also means that it's really easy to parse, because I can just reuse the same parsing for this as this. So I think this is how the functions are going to look. And then, you know, we just have return. And then I also really like the idea of just like having arrow functions. Like I think they're a thing from JavaScript, but it just makes sense, right? If you have a really small, not fun, we're not Go, whatever one it is, Groovy. Some language has fun as the function keyword, and I don't like it. You could have something like this, int b int, and then something like this. And then because the type of this is knowable at runtime, at compile time, you don't have to say what the function returns. And because it's just you're just returning a single expression, you can just point to that expression. And then it just fits on one line. So I like that this is how functions will look. So something like that. Anyway, our Gradle finally woke up and it ran. So now look, you can see we have a Java bytecode that corresponds to printing 10. And if I run it, it prints 10. Hooray. So let's ignore this arrow variant for now. And let's just try and implement... first of all, let's try and do a void function. By a void function, I mean just a function that doesn't take anything and doesn't return anything. Because that's just going to be the easiest thing to compile first. So we'll just wrap foo in... we'll just wrap that print10 in a function foo. And then we can just call it 4 times. Okay? So if we run this, it's going to immediately complain that it doesn't know what the hell we're talking about. Because, let's see, it expected a semicolon after this, because it thought this was a variable. And then it saw another identifier, and so it says, what the hell? So first of all, I think I'm going to add the... there it is. I'm going to add the new keywords to the highlighting just because it's easier for me. Like that. Yeah, those are the only ones. So now it actually highlights properly. Nice. So, to add a new construct to the language, you've seen this a million times before, but we just need to add a new keyword. And then in our lexer, let's make some room. When we're lexing an identifier or a keyword, we just add a new case and say when you see the string fn, why that's an fn keyword. So now if I run that, yeah, my parser now complains, hey, I didn't expect fn. So now we need to go into the parser and tell it what to do when it sees an fn. So a function declaration is a statement, it doesn't return anything. So that goes in here. So yeah. So after we get a fun keyword, so first thing we need to do is grab that keyword. And then, so what do we expect after that? So let's put the example over here. Let's have a look at this. So we next expect the identifier. So we'll just yoink that. So we've got an identifier. And then we want open parentheses. So where can I yoink open parentheses? Can't. So let's just type it manually, I suppose. You know, old-fashioned... old-fashioned streamer still makes code the old-fashioned way, whatever it is. Close paren. Close paren. Open close? No, close paren. Damn. Can you tell I just woke up? I'm trying to fit this in before work. Cool. So we would parse the parameters here if we were doing that yet. So I'm going to put a to-do. Parse parameters. And then, so we should parse a open curly and a close curly and a list of statements, but we already have a function that does that. I mean, we don't really have the function that does that, but we have code that already does that. So I'm going to yoink that out into a method, which makes that really nice. And then for that body equals parse block statement. And so that, in contrast to things like while, where I just say parse a statement, because with a while you can do, in fact I probably have this. So like you have the curlies because this is a block statement, but they're not required if you just want one statement. So I could go to my, well, first of all, this isn't compiling, so I'm just going to say, excuse you, yield null. And then in Jura, if I compile while.jura instead, much faster this time, and I run it, prints 10 forever, because I don't need the curlies. But for functions, I think that I think just looks wrong. I think you should have the curlies, and if you don't want the curlies, you should use the arrow function, which means you need to have a return type. So, I mean, you could probably use the arrows for a void, and then the type becomes void. I don't know. All that's to say, I want curly braces to be mandatory in functions. So, yield new function declaration statement. And that takes the fun keyword, the identifier. It takes the open and close parens. We don't do anything with them, but for completeness. And then we do this fun song and dance again. Let's make some room again. Yeah, we don't need that anymore because we've parsed it. So, put all these on separate lines because it's a large statement. Bind them to fields. We'll implement the method. We'll add it to the sealed, make it final. And then the span is from the fun keyword to the body. And so we want to have get body, get identifier, and that's kind of it. We don't care about the other bits of syntax. Yeah. And then eventually this is going to have the parameters, and it's going to have the return type expression. So, but for now, that's fine. So now our type checker is going to complain that there is a new type of statement that it doesn't know how to handle. So let's add that. And I think before we do that, I think we should think about what we are going to store in the scope. So I think, yeah, we're going to have a class function, which is going to be like the variable. In fact, it's going to be a record. Yeah, it should be a record. So what does it have? Well, a variable has a name, a type, and whether it's mutable. A function should have a name. It should have parameters, but we're not worrying about that now. It should have a return type, but we're not worrying about that now. So I guess that's it. But we will have more in the future. To do params, return type, and like other things like visibility modifiers like public, private, protected, whatever. Whether it's an override, stuff like that. Let's see, visibility, override, static, etc. But for now, that doesn't really matter. So we just want to get the span. Sorry, not the span. Identifier. Get the identifier. Actually, we just want the text, and that's going to be the name. So then we are going to create a function. I'm calling them functions when they could be methods on an object, but we haven't got objects yet, so I'm just going to call it a function for now. But we'll see. That's the wrong type of function. Yeah, calling it a function might actually be a bit of a problem. Yeah, that one. There we go. If it's going to collide, but I mean, we can just resolve that. And then in the scope, we have this map of variables to their name, and we need that for functions as well. And then we have these two methods that can find a variable going up the scope tree, or not tree, but like the hierarchy, and one that just declares a variable. We want the same, but for functions. So we want to be able to get a function. So basically we just need to say function every time you say variable. And if we also have like overloading, or like is it polymorphism? I can't remember. Where you define the same method with the two different methods with the same name but different arguments. This is going to not work because I'm only checking on the name, but don't care for now. I can just say to do method overloading. Yep, that all seems good. And then we just want declare function, which takes in a function, and we say does functions contain function name? If not, then we put into functions the function by the name, and we say that the function is already defined in the scope if we've already found it. Okay, good. So now we just say scope declare function. I might just make that a var just because it says function a lot. If that was successful, we can continue type checking the statement. So how do we do that? So we just do what would it be? Typed statement body equals type check function declaration statement get body. Boom. Goes through the entire function body and type checks it. And because we've declared the function before we do that, if the function references itself, so it's a recursive function, it will be able to find it in the scope. How about that? And then we just yield new typed function declaration statement. These are getting too long. And that basically just has the function and the body. Same way that the variable declaration has the variable and the identifier. So we'll create that in statements. And we do all this again. Ooh, too fast. There we go. Save these. Whoa, don't delete it. I want that. There we go. We want get body, get function. Cool. Now our lowerer is going to complain, which is fair because we need to lower it, or we need to lower its body. So just call that function declaration statement. We just want to say list of lowered statement body is lower the function declaration statement's body. And that's it. That will go through all of the statements and lower them. We want to yield a new lowered function declaration statement. Oh boy, which has the function and the lowered body. We don't want that semicolon. Implements list of lowered statement. Aha. No, it doesn't do that. It extends lowered statement, and I know why you did that. Just quickly fill this out. This has got me wanting to add some sort of Gen AI autocomplete to this, because doing this over and over again is getting a bit annoying, but I don't want it to intrude on anything else. We don't yield a new one of them, we yield a list of this. There we go. So now in our emitter, we need to emit a function. But we do something very interesting when we emit. We automatically wrap every statement in a main function so that we can run it. So if you look at what we emitted for the while loop, we automatically emitted this main function and then emitted the code that was inside while.jura inside it. It just kind of implicitly wrapped it in a main, and that was just so that it ran. But I think that we shouldn't have like free floating, scripted stuff like this. We should eventually have like proper, a main entry point and stuff like that. So I think it's a bit scuffed for now. But I think what we should do is, before we emit that, I think we should say for var statement in statements, if statement instance of lowered function declaration statement, I'll just say function declaration, we should emit this first. This is not how we're going to be doing it in the end, but for now this means that we'll emit all the functions outside of the main, and then inside here, if it is instance of that, continue. So we don't emit them twice. So then we just say, emit no, let's do it like this. So this is visiting the class, so we'll leave that above. This is visiting the main method. So we basically need to do this for this function. So the name is, let's get the function out of it. Yeah. And get its name. Easy. This is just going to be void. Doesn't throw any exceptions, and I think the signature thing is about generics. We're not going to touch generics yet by a long shot. And this I'm just going to call function visitor, just because it's technically a function because it's free floating, it isn't attached to any object. So we have this, and then we just want to say for var body statement in function declaration get body. We want to emit with the function visitor that body statement. So we're going to visit it inside this function, not the main method. And then we just need to clean up afterwards. Yeah. So yeah, we do actually probably want to reset the variables after this. Yeah. Okay, we'll think about that. But instead of main method visitor, we do this on the function visitor. Like so. So variables, we do that, and let's say variables clear. Cool. That should work. It's a little scuffed, but let's see. Will I one-shot it? Functions. So as a reminder, well, we don't have function calls yet. So, and let's put something so that we actually compile something and run it. Ooh. Switch statement does not cover. Oh yeah. Well. We could just yoink all of this and put it in there. I think we'll do that. So we'll say emit function declaration, and just say emit. Oh, it doesn't have a MV. Yeah, we'll add that missing branch. And then I'll just throw a new compilation exception. Oh, my bloody keyboard's in English again. And say this should have already been emitted. So if we ever get this exception, we know that something went wrong. Ah, come on. There we go. So we'll do that again. Unhappy. Yes, because we don't ever initialize functions anymore. Nope, compiled. Okay, let's see what we emitted. So we have this public static void function foo. Which takes in a single argument, which is a type void. I think, okay, I think in the emitter, where I said it took a void, I think it took that very literally, and so it should, in this, should just be nothing. There we go. It emitted the function. So let's call it. So I think here, let's call it a couple of times, and let's see what breaks. And I think I know what's going to break. We say unexpected token close paren. Why did we... Ah, yes, because we expect there to be a what's the word? An argument, because we only support print for the moment. So if I put this first, there we go. Methods other than print are not yet implemented. Well, now they are. But we should have a list of expression arguments. And we should say while cursor is less than token size, and do I have peak? Yeah. Peak does not equal token kind close parent. Parse an expression and add it to there. And you'd probably want to add a comma between them, but I'm not going to worry about that now because we're not having multiple arguments. So to do check for a comma, and then we pass that into, we'll call this, so actually let's refactor, rename this to function call expression. And that's very unhappy about this because we need to have a list and call this arguments. But there we go. That's probably upset other things. And probably just the type checker. Yep. So if we're doing a function call, yeah. So we just want to say we want to check the scope for if the function exists. So scope, get function call expression, identifier text. Let's yoink that out. So now we have the function. Then I'm going to say if function, no, if I say if name equals print, and let's also get the arguments, functional expression, get arguments, and the argument's size is 1. That's our inbuilt print function. We should do that before we try and get it from the scope because it doesn't exist in the scope. And we should just Yeah. Type check the argument. Like so. And then yeah, I think we should keep this typed print expression. We can do get first, sure, why not? But if it isn't, we should try and do it properly. So we get the function. If we got this, it means it exists. And then we want to have a list of typed expression. Well, I want to say if arguments is empty, if the arguments are not empty, throw a new compilation exception, function arguments are not yet implemented, which makes it really easy for us. So then we just have a new typed function call expression, which takes the function and a new array list, because we didn't bother checking any of the arguments. Yeah, we'll do that for now. That is a expression. Do all of this. Whoopsie doo. Do all of this. God. And then we want to add the constructor. And this is an array list of typed expression arguments. And there are no generics. Thank you. There you go. The type is actually, let's add it. Jura type return type. And we'll just hard code that to void for now. Whoa, I just want the, when we construct it, there we go. So function and then, what is it, unit type instance. There we go. So then the type is the function's return type. And then we want to have get function and get arguments. There we go. That should be it type checked. Albeit not very well type checked, because we don't actually check any of the arguments. We don't check if the function we're calling even matches the signature. But the only signatures we have now are takes nothing, returns nothing. So they should always match. That shouldn't break anything in the lowerer, because we don't lower expressions. But the bytecode emitter is now very sad. So we add a new expression switch. So this is going to be function call. Yeah. So we have this print expression. So this kind of shows us how we're going to call functions. So let's see. I think it was just going to be mv visit method instruction. And we're going to be invoking static, because it's a static function. Sorry, I thought I was going to sneeze. The owner is a fantastic question. Who is our current... I guess... if we put nothing for now, I wonder what happens. The name. So we need to get the function call function. And say it's the function name. And then we need the descriptor, which is takes nothing, returns nothing, and it is not an interface. That's kind of it. Assuming that this actually works. So if we run that, it does compile. Did it make anything? Looks pretty good. A legal class name in class file main. Okay, I think it has to be main. Where's my emitter? So if the owner is main, does it like that? What did that emit? Same. There we go. Okay. So it has to say, I guess it's saying that this is doing main.foo because it's owned by the main class, but it's static. Okay. That makes sense. Cool. Functions. And I'm pretty sure I could do bar, which then calls foo. And I can say, maybe it calls it twice, and I can call bar 3 times, and I should see 10 6 times. Very cool. So I think the next thing we need to do is add parameters and arguments and return types. So I think I'm going to make a cut. I'm going to come back later when I have more time, and I'm going to implement that. So I'll see you then. Okay, it's been quite a few days since the last bit you just saw, and in the interim I've kind of just implemented a bunch of things that weren't that interesting to watch on camera. Like now whenever there's a diagnostic, it prints it out in a list instead of throwing an error or an exception. And I've added a bunch of binary binary operators. So like bitwise and an OR, logical and an OR, bitwise XOR, and then for the meme of it, I added a counterpart which is the logical XOR. So instead of doing this for booleans, you do this. Kind of a meme. I don't think I'm going to keep it. I just think it's kind of weird that you have single pipe for integers, single amp for integers, and then double for booleans. But then for XOR, it's just a caret. So I did this, and then you kind of have a little uwu operator. But we'll see. That's basically it. I tidied things up a bit. I think since the last one I made all of these. No, these have always been like that. No, actually, no. I added Lombok, so that's cleaned up a lot of all these expressions. So that's caught you up. Let's get to implementing function arguments. So, what is that going to look like? So we have this horrible example here. Why don't we make foo except int, x as an int, and instead of just calling it like that, we pass in an argument. I think that's a good idea. So that means we're going to have to start parsing things like this. So let's do that, because we have all of the necessary tokens to actually lex that. So it's really just going to be in the parser. So let's just see where it fails, and I'm going to have to switch over to functions. And this is going to take ages because it hasn't actually been ran in days, so we'll have to wait for that. So let's see, where is it probably going to fail? It's probably going to fail in new function declaration statement. And no, here we even have the to do. So it's probably going to say, oh, I expected a closed paren, but I got something. But it didn't. But it didn't do that. Why did you build successfully? Ah, yes, because we don't throw exceptions anymore. We report diagnostics. And so currently they aren't very useful, or at least they're not very pretty. Like, offset 7, length 1 isn't very useful. Like, I guess, close that. Like, I can infer that's here. Yeah, like, column 8, so that's offset 7. But it'd be nice if it, like, got that line of the code and then highlighted the exact span, which, if you've watched do, is exactly what do does. But I haven't implemented that yet, which is fine. So yeah, it expected a closed parenthesis, but it got an identifier. So we need to It's a list of, call it a state, no, not a state, a statement, parameters, like so. And then we just say while peak does not equal close paren. We just say parameters add, and let's just make a method for this. So we'll say parse function parameter, and to do expect comma, because I think we have somewhere else where we take a list of things and then we expect a comma, but we haven't actually implemented that yet from memory. Yeah, what is this? This is when we're parsing function calls. Yeah, so exactly the same. We don't actually have a comma token yet. So let's implement this. So what do we expect? We expect an identifier. We expect a colon, and we always expect a colon because you can't infer the arguments. You probably could if you were smart enough, but I don't think this language should allow that because it's just simpler if you say, oh, this is an integer. And then we expect a type afterwards, which for now is just a single identifier, but that isn't always going to be the case, and I don't know why I closed the example, because this could be like an array, which is multiple tokens, or it could be something more complex in the future, like, you know, we could have like generics and container types, stuff like this, where you have like, you know, really complex types. So we need to be able to parse these things. So I think it's probably a good idea for now to kind of like put the parsing of the types into a different function. And these are going to be probably a statement, because they don't really... Ooh, actually, I think they're going to be expressions, right? Because this, I think, is going to return a type of type. So, like, you could have something that's like, you know, like maybe this is how we do casting, right? And we say we cast x to int, something like that. You know, I mean, it's already an int, but go with me here. So the second argument to this like hypothetical method is of type, and so we need to be able to parse types as expressions. So I think it makes sense that we do this. I'm going to say parse type expression. And I think it might make sense to actually just say that this is a type expression. And I think it should be its own class of expression. Can I do this? So what I mean, right, let me implement this and I'll show you what I mean. So where expressions, I got confused by the fact this is all typed. No. So that does mean eventually we're going to have a class called typed type expression, which is ridiculous. Anyway, so if we have a type expression, well, an expression is a sealed class, and that allows us to do things. Can I put these on new lines, because otherwise it's kind of ridiculous. That'll do. It permits all of these subclasses, which then means you can switch on an expression and it will fill out all of the cases and then automatically do the cast for you. I want to do the same thing here. So I'm going to say this extends expression, but I want it to be itself an abstract sealed class, and I wonder if it allows me to do that. Sealed class must have subclasses. Okay. Let's make a separate package for this. Yeah, let's call it just types for now. So currently the simplest case we have is let's just call it a basic type expression for now. Let's make it final. and this extends type expression. So that has to implement get span, has to do that. Okay, that works nicely. So now we have a specific type of expression that is still abstract, and then we can then switch later on what type of type expression it is, because we could have like an array type expression, or a generic type expression, or something like that, right? There's several ways. Or we could even have like slices if you wanted to go that route. That'd be a separate type of type expression. Yeah, and because this is abstract, it doesn't know how to do its span. So that's up to this one to do. And all a basic type expression has is a token. That's all it is. And so we return the token span, and it has a getter. And we can just give it an all args constructor, and that really shrinks it down. Lovely. So let's add this parse type expression. And actually, we should probably go and update variable declarations while we're at it to return a type expression. I think that'd be a good idea. So, currently, all type expressions start with an identifier. So we will say expect next identifier. And then we'll just return a new basic type expression with the token. And I'll say to do arrays generics maybe slices. I don't know if you heard that, but that was my dog just like letting out a little groan. He's snoozing. He's got a little bed in my office behind me, and he's just curled up and absolutely snoozing. So we'll return a new, so we'll call this type. No, this is a function parameter statement specifically. So that has an identifier, a colon, and a type expression. So we need to make that. Cool, cool, cool. Well, let's do this quickly. And we'll say this has a getter, and this has an all args constructor. It implements get span, and the span is from the identifier to the type expression. What else? And it needs to be part of that, and it needs to be final. Cool. So we have one of those. So let's go to... so we're going to parse the parameters, but we don't do anything with them, and also we don't expect commas. So if we go to variable declaration, there we go. So yeah, we have type identifier. I mean, yeah, it's already optional. Cool. So instead of a token, this is a type expression, and so let's call it such. And so we'll say type expression peak. Yeah, so we're kind of saying here that we expect that all type expressions start with an identifier here as well. Okay. So the reason why I'm saying that is like I'm kind of undecided on the syntax of certain types, because I kind of like the weird type syntax of like Odin, I think, or like Zig, where like an array, instead of something like this, it's like this, and it kind of helps when you have really complex types. You just read them left to right, and I think it's less of a problem for this language because, like, say you had pointers as well, you would read this left from right, and you would say, oh, this is a pointer of array of integers, right? Whereas if that was in C, you would have that, and then I think the pointer would go like here, or like the star would go there, and so that's a pointer of int array. It doesn't read as cleanly, and then as that goes on more, like you could say, oh, this is a is that right? I don't know, C. But basically it just reads nicer. But I think because this is going to be Java-like, I think this makes the most sense, just to have like Java-like types. So I'm going to leave it like that. So we say that they must always start with an identifier, but I will add a note. This assumes that all type expressions must begin with an identifier. Yeah, that'll do. And then we need to change the variable declaration statement. So instead of a type identifier, this is a type expression. And that's going to break something in our type checker. But I think now our type checker actually gets a little extra like information. So like instead of saying that it's parsing a token, yeah, so parse type, yeah, it now can specifically say, oh, this is a type expression. And then we have to switch. And look, we even had a note. This won't work for complex types like arrays which need recursion. So yeah, we can just say, oh, we'll switch on the type expression. And yeah. And now we have an exhaustive case. Sorry, I just looked at my camera and I'm like really dark. Let me turn my lamp on. Yeah, that's better. Yeah, I also I always have to have my curtain shut because if I have it open, like you can't see me. Oh, it kind of adjusted, but yeah, it's just better if not. Anyway, so now we have an exhaustive match. So like if I add a new if I add a new type expression later that's not just the basic one, this is going to have a compile error, and I know I have to come here and fix it. So in here, we basically do this, and we say get token text, boom, and then okay, now I need to update the diagnostic. No, I don't need to update the diagnostic because what did you take? Oh, you took the token. Okay, let's just give it one of those. There we go, and that's completely exhaustive, and then that should keep working. Yeah. Now it's going to complain that we aren't type checking type expressions. Okay, we'll get to you in a second, sir. Let's go back to the parser. So where were we? Parser is compiling. Parsing variable declarations. So let's go back to function. Crikey. Nope, not like that. There we go. So we're parsing parameters, but we aren't putting them in here. So we'll do that. And one moment, my cat is crunching. There we go, she's finished that. So we were adding the parameters to the function declaration. So we'll add that as a argument, and it's still not happy. Identify open, okay, whatever. List of statement, parameters, and we can be more specific so that this isn't annoying. So this returns a statement, but let's just say it returns a function parameter statement, and that these are always function parameter statements because that's what they are, and that way we don't have to then resolve what kind of statement they are and have a bunch of cases that'll never happen. We can just bake it into the compiler. So cool. That's going to have very much upset my type checker. So let's go see what's going on in here. First of all, we have a new kind of typed expression. Yes. So type expression, type expression. So I think we probably want to do the same thing in here, because I think we already have a types. I think actually, yeah, I think I'm going to keep these at the top level and they'll just sit there like that. And then we can have counterpart, which, as I said before, is the typed type expression. Ridiculous. Which extends typed expression, but it itself is an abstract sealed class. Add it to the permits, and it's going to be typed basic type expression. Maybe basic typed type expression. That's a horrible name, but we'll go with it. This will be final. It'll extend typed type expression. We'll implement get type. Very cool. And it will add it to that. So the Jura type of this is going to be type. Is that a good idea? Stringify, add type, make it final. I think this is just gonna hold a Jura type. So stupid. I don't know where I'm going. I don't have a plan. I'm just like following where this is going, and I'm going to see where it takes us. So the stringify is going to be, I don't know, something like this. Sure. So the basic type expression returns. So this is going to have a final Jura type, and it's going to this will be not type but Jura type, so it doesn't conflict with this. And it will be return a new type of that Jura type. This is very stupid. Okay, so all that means is if we get a type expression, and so the only time we're going to get an expression like this is in the case I was saying before, where we could have it that you know, I want to say B is like casting this X to a bool, right? This is a type expression of type, but it's generic in the sense that it has a type in it. So this would be a type of bool. Does that make sense? Right? So the signature of the cast function would be something like cast T T, and then like type U type, right? And it would have two generic types, T and U. Does that make sense? And so this would resolve, and it would return a U, right? So this type U resolves to like type bool, which is this thing, right? That's just the string representation of what I'm trying to say. And then the T is an int, and so this resolves to int and bool, and so the result of this is bool, and then that's what this cast is doing. Okay? So what I'm implementing now here in this type checker probably won't ever be a thing for like ages, and that's assuming that's how cast is going to look. But I mean, like that's probably going to be like more applicable to things like when in Java you accept something like class T as a parameter. Maybe for like serialization, that's probably a better example than casting. Okay, all that's to say is we need to get the Jura type from parse type from the type expression, and then yield a new type basic type expression with the Jura type. So actually, we need to future-proof ourselves here. Switch on the type expression and say case basic type expression. Oh, come on, you can type better than that. And then that's this case. Right? Why is it unhappy? Oh, yeah. Because this needs to be a return. And that then needs to have a semicolon. And then it's still very unhappy. Return outside of enclosing switch expression. this needs to be a yield, which means it can be inline. Java 24 is such a different language than what I'm used to from Java. I've been coding in Java for like nearly a decade, and I'm so not used to this like cool, actually useful syntax. I'm used to it like just being pure pain anytime I want to try and do anything like this. Okay, so that's parsing type expressions. We'll probably never hit that line of code for a very long time. So now, function parameter statement. Yes, so this one. We just want to type check the type expression in it. So actually that case that we just implemented, we're going to hit exactly here. So we want to type check the type expression. And that gives us, yeah, a typed expression. But it's specifically going to be a typed type expression. And I think we can make our lives easier if we specifically do that. So I'm going to yoink this into a method, and that's going to be type check type expression. And that way I can be specific and say this is a typed type expression. And then up here, instead of calling type check, I can say type check type expression, and then I get a typed type expression. Oh, I'm sick of saying the word type. This is so stupid. Okay. Oh, now this is interesting actually, because what do we do with the identifier? No, not a constant, a variable. Meow to you too. She's getting up to mischief. Because, so if we go to function declaration and we type check the body, we are declaring a new scope. So if we go into here, we're declaring a scope in which there is a variable x, and x is of type int, and we need to tell our type checker that there is going to be a meow. There is going. I hope you can hear, and I'm just not just meowing into the void. There's going to be a variable called x. So we need to say, okay, scope declare variable. Yeah. So let's say variable. No, we're going to do this the fun way. Var variable equals new variable, which takes the identifier text as its name, the typed expression. Is that what we want? You are getting up to mischief, aren't you? Yeah, so typed type expression. Yeah. Hello there. I think that this should actually be a property of typed type expression. Like so. And all as constructor. Sorry, she has now jumped onto my lap. One moment while she gets comfy. There we go. So basic type expression. This actually doesn't need to be in here now either. So what do you do exactly? Why are you unhappy? Constructor matching super. Sure, there we go. So now we can say get Jura type. This is confusing, isn't it? Because get type gets the type, whereas get Jura type gets the underlying type that this type expression represents. Yeah, that's very confusing. And I'm going to say it is not mutable. Is that a good idea? I'm going to say it's not mutable. Not that we check for mutability actually. In like a variable like reassignment, which I think is actually a binary expression somewhere. Yeah, we don't actually check for mutability, but we're going to declare the variable, and it takes a span, I believe. Yeah, because if that variable already exists, which could happen, if you do this, right, it's going to say, oh, but there's already an x in scope. So the span is on the function parameter statement. Okay, we return a new typed function parameter statement, which just takes the variable. And we do this fun song and dance again. I love Lombok. It's so much better. Cool. And we also need to... So that automatically declares the variable in scope for us. So all we really need to do in the function declaration statement, before we type check the body, we need to make a new scope. Because if we don't make a new scope, we're currently outside of this scope here. So if we start declaring x as an int outside that scope, if we had another function that had x as an int, this is going to clash with this. So we need to kind of wrap the whole function declaration in its own sort of like anonymous scope. Is a new scope, and the parent is scope. And then we just say for var param in function declaration statement, get parameters. We type check param, and we get yeah, it's probably easier if we do the same trick here. Whoa, it didn't like that. This will be type check function parameter. Yeah, there's no need to be saying statement all the time. We know it's a statement. Like so. That's nice. So in here we can just say type check function parameter, and we get, let's get a list of these bad boys. I'll just say params. Add that. And then we can just stick that. Ooh. Ooh. Yeah, we should add that to the function declaration, actually. So we should actually be declaring the function down here. But that means we're only declaring the function... Oh, that's fine, because this is for recursion. Yeah. Okay, so we're going to have to actually declare the function twice. And you'll see why. So we open a new scope, we type check the params, and then we put the params inside here. And that's a record, that's easy, so we just add that as a argument to the constructor. So we've done that, we declare the function, we type check the body, and now we need to leave that scope. Like so. Okay, so to make this a bit more obvious, we can actually just use this kind of thing. Well, actually no, that's kind of wrecked the whole thing, because we do actually need that. Okay. So yeah, we declared the function inside this scope, but now we're in this scope, so when we yield this and move on to another one, it now is outside of the scope. So we actually need to just... So I'll say declare inside the function scope for recursion, and then declare outside the function scope so other functions may call it. Does that make sense? I don't know why I'm asking you. You can't reply. Unless I was actually like streaming this, which is an interesting idea, but I feel like I make way too many cuts to actually stream. Also, I don't get enough viewers to stream. Not that I'm complaining. I mean, I'm just doing this for the love of the game. I'm not doing this to get like millions of views. I'd hate to have millions of views. That'd be stressful as hell. Okay, so we've declared a function, and we've type checked the parameters, and we've stuck those inside the function object, which means, first of all, our lowerer is going to be complaining because I've just added new statements, but there's nothing really to lower. I just punched the microphone, sorry about that. There's nothing to lower, which kind of means we're never going to see this. So I'm actually going to throw a new compilation exception and just say lowering per function parameter statement, because I don't think that should actually trigger like that. Why are you complaining? Because there's far too many semicolons at the end of... Why is the hitbox on that scroll bar so big, huh? Cool. That's happy. And now the bytecode emitter is going to be complaining. Type expression, get type. Because I have a new type, which is the type. So if I wanted to print a type, I'm going to have to print the name, which is going to be a string, which is a complex type, which I haven't actually started dealing with, so I'm just going to throw a new compilation exception. Printing types is not yet implemented. Easy. Just slap that bad boy on anything and you're good. And then if we're, then if we're doing a type, ignored, let's say variables of type are not yet implemented. Easy. And so now we need to emit, let's see, what have we got? Type expression. Well, what do you know? We don't actually emit those yet. So I'll throw a new compilation exception. And it'll be emitting type expressions is not yet implemented. Cool. What we haven't done is actually emit the parameters of a function. There we go, the emit function declaration. So we get the function. And here's the part where we actually get the descriptor. So the descriptor here, I'm saying it doesn't have any arguments. So what I need to do is probably sort out this signature. Is the signature to do with the arguments, or is that generics? I thought it was generics. Yeah. See? Because this is done by like the variable index. This is to do with generics. So what I need to do is have a function which is build function descriptor, which takes in the function as a whole, because it's eventually going to have returns as well, or a return type as well. And that builds a string. So let's say string builder sb equals a new string builder, and then it will return sb to string. This will start with append an open paren, then there'll be a close paren, and then that, and I'll just say to do return types. So in here we'll say for var param in function params, we need to have something to figure out the type descriptor. So let's say sb append build type there. Ooh, sorry. I'm resting my arm on my cat's head, and she didn't like that. Now she's resting her head on my arm, so typing might get even harder. Build type description from the param variable type. There we go. So this will be a string from the type. We switch on the type. We want to return that. Create the missing branches, and here we go. So bool is a z. Error. This is throw new compilation exception. Error type should not be emitted. Int is an I. Type. We aren't concerning ourselves with that yet, so I'll say emitting type is not yet implemented. That's going to be a very confusing error I'll get one day, so let's move these to the top. Unit is a V, because that's void. And there we go. And this is exhaustive, and it will support recursion. Because if I have a type which is like array type, which I'll have a type inside it, so like the same way that type does, I can just call it again to get the type of the elements, and then I can say, oh, this is a a list of this type, or like whatever the syntax is. This is an array using it's just using the square bracket. Cool. And then these are all ignored, so I can probably do something cheeky like that. Cool. So that builds the function descriptor. So actually, that should do it for function parameters. And I think that does it for... We already have function arguments because of print. So what happens if I just send this? Yeah, standard. Function arguments are not yet implemented. Well, guess what, man? They are. Well, maybe they aren't. Okay, let's just finish this off. So if the arguments is empty, not empty, boo, don't care. What do you take? Yeah, you just take a list of typed expression arguments, function call expression, get arguments, stream, map, arg to this, type check arg to list. That can be a method reference. Boom, boom. Arguments is already declared in scope. Where? So these will be checked args or something. And then I don't have to do this, I can just say arguments. And then pass those in there. Why are you specifically an array list? That's not good. Cool, and then the bytecode emitter isn't complaining. If I look for where function call is, yep, that makes sense. That gets the function. Yep, so we need to build the function descriptor of the function. There we go. No diagnostics. So what does our emitted class file look like? Couldn't be decompiled. Do you know why? Because I don't declare the variables in the function. So let's actually simplify this way down to just that and foo10. So let's compile that. Couldn't be decompiled. Interesting. So that's, I already know that there is one problem. So if I fix that, does that fix it? So function declaration. Commit function declaration. Function name. So before the body, for var param in function params. Param get variable. Do that. We need to say, do we just have a, yeah, we have a list of variables. Just add the variable. Okay, seems happy. Okay, there we go. So the reason that works is because we declared the variable, we need to like tell the bytecode which variable to reference when we reference it in the code. So it's the 0th variable. So in the bytecode, the offset is 0. This is very unhappy though. Why is this unhappy? Let's try and run it and see if it actually just tells us what's wrong. Attempted to pop an empty stack when we were invoking static. Ooh, okay. So what do we do when we do a function call? So we're invoking static on main, function name, function descriptor. So this was this. Yeah. So see, I'm calling it... I never emitted the arguments. That's why it's saying I'm popping an empty stack, because I'm telling it, hey, there should be an integer that I'm passing in here. Is there an integer on the stack? No. So var arg in function call arguments, just emit the bloody argument. There we go. Now we're emitting the argument. And I've lost my Jura file in here. There we go. So we're doing that. If I run main, it prints 10. So let's go back to our more complex example where we have zero arity functions and then unarity, I don't know, functions. Let's check the emitted bytecode. Let's get rid of all of this noise. Seems very happy. This seems pretty correct. Will it work? Functions, baby. So I think the next thing we should probably do in the little time I have left, because I need to stop in about 20 minutes, is this, where we can have a comma, and then I can do that sort of thing. Compiling this. Well, let's do something. First of all, let's prove that we can reuse variable names, and we will not call it x inside here. We'll call it I. There we go. So let's try and get this wonky example, and then we'll pass in to bar 5. So we'll like offset the count by 5 for every call. So we need a new token. A new token kind, rather. Let's make some room. Let's put it after semicolon. Yeah, comma. Lexa. I also added another helper function to Lexa, which is for lexing double chars. So it says, you know, if I see an open angle and then I see an equals, it's an open angle equals. Otherwise, if I didn't see that, it's just an open angle. But thankfully, this is a nice, easy token. And then in the parser, this should be nice because after we parse, we don't need the comma again. In fact, we don't even need to save the comma, we just need to know it exists. It's completely superfluous. There's no reason we should even need a comma. Yeah. Like right now, I could just do this, I think. It didn't complain. Yeah, like it knows that the parser knew where the expression ended, and that's when it knew to then like come out and then parse another one. But like that's just very like you know, weird in the language. So like we insert the comma just for the programmer. So I just need to say if peak does not equal close paren expect next comma. That's it. And then in the other place where we expect a comma, we do the exact same thing. Whoa, that's a lot of diagnostics because I don't have commas. There we go. And it didn't offset everything by 5. Oh, because I only passed 1. I know, yeah, it offset it by 1, so that did work, but I coded the Jura wrong. There we go. Started at 5, ended at 14. And you'll also see we got to reuse x because we did that stuff with the scope. If instead I declared x twice in foo, variable x already defined in scope. Maybe I should have a different error message for function parameters, because I'm pretty sure Java would have something like that. If I find, like here, if I declared string program again, variable program, even Java says that it's a variable. It probably does the exact same thing we've done here, which is we just reuse the variable declaration type checking. Not bad. That's pretty cool. And I actually kind of like how tidy functions look. How about that? We are missing returns. So if I do something like fun sum, a int, b int, I don't have this, but I think we have all of the mechanisms necessary to just do that very quickly. You know what we don't have though is a return statement. So actually I think that's probably a bit more involved. So I think I'm going to take a break now and come back later this afternoon when I have more time to implement this. Because what I want to do is, well, first of all then is I can replace this with, you know, that to prove that that works. And then I kind of want to have a syntax in this language. I think I've mentioned it before, of like arrow functions, where if the body of a function is just a single return statement, I want you to be able to do something like this. So if I just say sum2, not that I'm going to be able to compile this yet, but so later it doesn't clash. And then look at that, I even forgot the comma. Instead of saying int, you just do a fat arrow to an expression statement. And then this just implicitly means return this. And because it's a single expression statement, we can just type check that expression, figure out what type it is, and then say, okay, well, that's the return type of this function. I don't know how useful this would even be in the real world, but I really like this syntax, and I think it kind of then informs how you do the syntax for like a anonymous function, or like a lambda or something. So say you have a function map that takes in like, we'll make it ints for now, like that, and then maybe a function of like int. Would that be the syntax? I don't know. See where I'm going? Okay, so you have this kind of function, and you wanted to call it, so you would say like map. Well, this would be like a method on something, so something like that, and you would call that mapper. Let's see. It kind of feels like the same syntax. Again, does that make sense? Like, it's in my brain, and it's hard to then express in a way that like makes sense aloud. Basically, this syntax matches this syntax, so then the language has kind of like some internal consistency when it comes to like implied function returns, like the return types. I don't know. You tell me. So, I'm going to take a break. I'm going to go do what I need to do today, come back, and then we'll finish implementing this, which actually is going to open another can of worms, because, you know, what if we say it returns an int and then we never do? So we have to do some sort of checking on the body to make sure that it returns a value, and then we can have some fun with arrow functions. So I'll see you in a bit for you, a couple hours for me. So, it's now several hours later, as evidenced by the fact that I'm now in a jumper. So let's add returns. So the first thing we need to do is add a return keyword, which is very simple. You've seen this a million times before. Well, you've seen it 6 times before. And there we go. We now have a return keyword. And let's actually simplify this so that we, yeah, we're actually just compiling this. So, what do we need to do? In the parser, so return is a statement. So we need to check for it when we're parsing a statement. So let's go down here and say case return keyword. Very simply, we just expect, let me move my mic a little bit away from my keyboard, that's probably very loud. We expect a return keyword, and then we either expect a expression or we don't. Because if, say, this was a void function, or like here, you know, we should be able to just do this. Because, you know, we could say if x equals 10, return. And this is a void function, so it doesn't actually return anything, so this needs to be valid as well. So let's keep this in, so we can test both cases. So we have the return keyword. If we peek and it does not equal, excuse me, a semicolon, expression equals parse binary expression. Yep. I should probably I should probably just have a parse expression. Yeah, let's do that. Let's make it private, because I don't think you ever want to just parse a single expression. So I'll just say private expression, parse expression, return parse binary expression 0. Just because it feels weird to always be like, oh, parse a binary expression when you just want an expression. So where were we? Where were we? Here we were. So we just want to parse an expression. There we go. And we want, yeah, you are quite right. We want to just do this. If there is no semicolon, we do that. And then we expect one. And then we yield a new return statement with return keyword, expression, and semicolon. Easy. See, what I really like about when you set up these compilation steps is like adding new like features to it is so easy because you just have all these pieces to build stuff out of. Like you're like, oh, I need a new statement. You have, and like, you know, what does the statement have? It has an identifier and then an expression, and you can just add that. Like you can have like parser generators, and you have to like write it in some weird language so that it generates this stuff, or you could just write it. I feel like that's the fun. Is just say, oh, this is what the syntax of this statement is. Oh, that's what it's made of. Boom. Easy stuff. So let's just add all of the stuff that we need. Come on. Make it final. And then we add in this stuff. I swear half of these videos is just me clicking all of the autocomplete stuff. So then we don't want any of that. We just want to have a getter, and we want to have an all hours constructor, and the span is from the return keyword to the semicolon. Easy, easy. So that's the parser. Now we need to type check. Yep. So up here, this is where things get a little interesting, because currently the parser doesn't make any kind of check to see where you're returning from. Like you could do this and the parser would be fine with it, but you need to know like whether you're inside a function or not. So I think what we need, maybe this is a bad idea. But here's what I'm thinking. We have a context. Excuse me. And that context is going to do us several things, I think. No, I don't think it will. I think we're just going to have one thing, and then we're going to have a private function, current function. Maybe that's a bad idea, but we'll see. So that will just have a getter and a setter on it. So when we parse a return statement, we need to do scope get current function. So I got confused by that get function. Current function. And we say if current function is null, then we report a diagnostic. And this is how we report diagnostics. I haven't actually shown you how to do this. So every one of these extends compilation step. And what this is just has a list of diagnostics, has a method, has diagnostics, and it can report diagnostics. And what happens in the main class, in the Jura class, is after every compilation step, we just have this check, basically, which takes a compilation step. If it doesn't have any diagnostics, it returns. If it does, it just prints them all and returns true. And that way, if we return true, we can just stop compiling. Maybe not the best solution, but it works for now. And then eventually we can come in and we can do something a bit more sophisticated with displaying the diagnostic, like finding the line that it happened on and highlighting the part of the program that caused the diagnostic. But for now, this is fun. So we want to report a diagnostic, which has a static, a set of static methods. We're going to have a new one. So let's see, what does Java do? Or what does Java say if I put a return outside of a function? It's just an unexpected token. Maybe it does happen inside the parser. So we could reject it at the parser step. So would the parser have a current function, or like is in function? Because I know like you can have certain flags in a parser to say like whether you're allowed to parse certain things or not. Like if you're like having like a a struct literal syntax where you can just say like, you know, foo equals and then some struct. You can have certain flags to toggle whether you're allowed to do this or not, so that it doesn't misinterpret this as like a block. We can do something similar. We can have flags. So like private boolean allow returns equals false. Kind of redundant, I know. And then we go down to here and we say if not allow returns diagnostic unexpected token, and we could just pass it the return keyword because then it can yoink the span from it. Why isn't it like that? It might be null. That is true. But it can't be in this case because we've already peeked and seen that it's a return keyword. So that's fine. Yeah. There we go. So we don't need to do that because current function is always true. But it isn't because we never actually set allow returns. So we need to say when we see the fn keyword, when we go to parse the block statement, we say boolean allowed returns equals allow returns, and then we say allow returns equals true, and then we say allow returns equals allowed returns. Just in case we're like nesting, this doesn't then like overwrite it. Like if you have a function inside a function, for example. Variable allowed returns. Did I mess up? I did. There we go. Thank you, compiler. Very helpful. Okay, so we now check that inside the parser. So now if I were to do that, it would complain in the parser. So I'll leave that in for now, and then that will trip us up later when we actually can run this thing. In fact, if I do yield null now, everything should compile. In the sense that, like, the Java program should compile. Expected open curly book colon. Yes, because we don't actually parse this yet. So let me get rid of that for now, and then just run this. No function sum. Ooh, you're a tricky one. Okay, we'll do that. We'll do that. We'll do that. Complained at the lowerer, which means it got through. Interesting. It managed to get all the way through. Did I not report the diagnostic properly? There we go. No, I'm going to leave that. Can I hide that? Oh, it doesn't matter. Okay, I don't know why that doesn't work, but that's fine. That's not what we're testing right now. There we go. But that is a good point. We don't parse the return types on functions yet. So let's do that before we finish up in the parser. So when we get a function, we parse the body here, we close paren, which is here. So we need to see if there's a colon. If there is, we need to parse a type annotation. So close that. If peak equals a colon, we expect next colon. We can throw away that token because we don't really care about it. And we want to get a type expression. And this is the return type. So I think we should have one out here and we should assign it null. Yeah. And then return type equals, is it just parse type expression, and then we don't need to declare it. Cool. So now we have the return type, which goes after the close paren. So we can just add it in here. Add it as that. Did it not? Yeah, it gets confused because it's all lomboked. Final type expression return type. There we go. So now we can parse all these things. So if we go to the type checker, I'll leave that one broken because this should be very easy. So function, we already have a return type and we just hard code it to the unit type. So we do already handle that. We don't omit it properly, I think. Maybe we do. We'll check that in a second. So we get that. Parameters. Yes, we should do it here. So I should say var return type equals function declaration statement get return type equals null question mark. If equals null, that is a unit type. Otherwise, that is parse type, like so. And then we just pass that in instead of a unit. Boom, easy. And then if that can't be parsed, it will raise a diagnostic. Does it raise a diagnostic or does it... Yeah, look at that. And it returns an error type. Sick one. So now we can go back to this return statement. So we get the current function. We say if current function return type. No, we should say if the return type equals unit type instance first, we should say if return statement get expression does not equal null. So what would that mean? So if we had a function which is void, or foo, and we said return 10, what does that say? Cannot return a value from a method with void result type. So it's got a unique diagnostic. So let's say cannot return value from void function, or from cannot return value from unit function, because we're using unit in this, which is very Rust of us. Hello, Aria. Wait, where is she? Where is she? There. Hello, Aria. Cannot return a value from a unit function. And all this is really, yeah. Oh, look, it even has a hint. We should add hints, actually, to our diagnostics. But not yet. And so we just say return statement span. Let's add that one. And so we just return a new diagnostic. Cannot return value from function with unit return type. Just like that. However, if instead this actually did return an int, and I said this, missing return value. Okay. So if current function return type does not equal unit type instance, and if return statement get expression equals null, we do the same. Diagnostic, what was it? Missing return value. And again, return statement span. Okay, and then we add this one. Return. Oh, yeah, return new diagnostic. Missing return value at the span, and we forgot to actually report it, which is why it did it as a void. Okay, these can be very much simplified. Whoops. Is it going to do it for me? Merge nested ifs. Merge nested ifs. Can we do anything fancy with this? No. I don't care. It's fine. Let's make some room. Okay, so we're definitely inside a function, and we definitely are returning something if we should, or we aren't if we shouldn't. Let's see. Maybe we... Okay, let's split this one. Because... come on, just put the braces on. Because if it is if it is a unit type return, and we don't have a expression, that's correct, and we should just yield a new typed return statement with nothing, basically. Yeah. Otherwise, we need to typed expression. I'll just call it expression. We should type check the return statement expression, and then we need to check if expression get type equals current function get return type. If it doesn't, diagnostic type mismatch. We expected the current function return type, but we got the expression type at the return statement span. Actually, at the return statement get expression span. Cool. Yep, that is always true. If that is null, we should also yield that just to keep going without causing any errors. So yeah, we've raised that diagnostic, so then we should just yield a new typed return statement with the expression. Cool, so we're going to have two different constructors, and let's clear this up before we forget. So let's create this in statements. Cool, so we're going to have a private final typed expression, and we're just going to assign it here, but we're also going to have another constructor which takes nothing and just sets it to null. Cool. And we don't need the all args constructor. The all args constructor, because we need to do it like this. So what's your problem? You're dumb. That's your problem. Okay. Think about it for 2 seconds, please, compiler. And that's it. Oh, that's nearly it. There is one more step, but that's not going to hinder us at this stage. So that has added a new statement to our type checker, so our lower is now going to complain. But I think... yeah, let's do that. I think we just want to return, or what is it? Yield a list of new lowered return statement get expression. That's it, really. And then because of that, we don't even need the yield. So we'll add that. Cool. And then we'll add a getter and I guess an all args constructor, and we can throw all that away. This extends lowered statement, and then this has to be final. Come on. So expected 0 arguments, did you? Yes. There we go. So if it was a null expression, that will just pass it null. Otherwise, it will pass it the expression. So now in the bytecode emitter, this will be very simple. We just add the missing switch case. If it's a return statement, we say if return statement get expression does not equal null, emit that expression, and then we need to visit just return. I believe, yes. I don't know what ret is. I think ret might be for jumps, not for methods. I'm not entirely certain. And there's no doc in this. Ah! There's different returns for different types. Okay. So if it doesn't equal null, we actually need to switch on the expression type. Oh, I've lost my mouse. There we go. Cool. So these two. Yeah, okay, never mind. If it's a unit, you visit return. These are all ignored. I wish you could just not... I wish that was legal. That makes sense. If you're ignoring it, just let me not put it. Hey, okay. If it's a bool or an int, and like, because you can't do this, it means I can't collapse cases. Ooh, let's get rid of that. Get rid of this, get rid of this, and these are both I return because a boolean is just an integer. Type, we can actually do this one already because this is just going to be an A. An error type should be throw new compilation exception. Should not return error types. Well, yeah, we should have gotten rid of it by then. Let's make these all ignored, and then we return so that we don't emit that second return. Okay, so let's remind ourselves of what it is we're compiling. All of this. So I think we've actually implemented enough for this to all work, but let's check. Yeah, I didn't think so. Cannot invoke get return type because current function is null. Quite right. I never set it. So if we are declaring this, we go to type check the body. So before this, we say scope current function equals. Wait, can we just say set current function? I know it's absolutely fine to just call it on the parameter or on the field, but something about it just feels wrong. And then scope set current function null. There we go. Any more? One more. Cannot invoke current function is null. How? This might be why the parser part wasn't working. Something feels amiss here. Why would current function be null in the return statement? Well, first of all, I don't think this is it, but we shouldn't be setting it to null. We should say function outer equals scope get current function, and we should reset it to outer first of all in case we're nesting, but that shouldn't be it. This should still, yeah, this should still fail. we're setting the current function, and then we get it here. So let me put a breakpoint here. Scope. Current function is null. We don't check recursively. Okay. Right. So we need to do this trick. Okay. Public function get current function if current function equals null and parent is not null. Return parent get current function, otherwise return current function, because then if it's null and we don't have a parent, just return null. If we have something, we return it, and if we don't have one and then we have a parent, we'll ask the parent. There we go. Okay. What did we generate? Did we generate anything that compiles? No, we didn't. Okay. So it thinks that sum is void, despite the fact that we have done this. So if we go back to the parser and we look at how we parse this, return type is null if peak equals colon. So let's go here, because the first one we should do is sum. So fun identifier sum. So peak is a colon, and we set the return type to a basic type expression of int. Okay. Cool. In the type checker, what is it? It's function declaration. So come into here. So this will be sum. Yep. Create a new scope. We'll check the params. Return type is an int. Oh, I know why. Because we don't set the signature in the emitter. See, we even have a to-do. And that's very easy because we just append build type description for function return type. There we go. Look at that. We return an int. We're returning var1 plus var0. Foo is void. And then it like reverses our early return, so it only runs the body if it isn't 10, even though in our code we say if it is 10 return. That's very cool. Okay, all right. So we should. So if I up this to 20. So what's going to happen? We're going to start with 5. I is going to equal 5, and we're going to print 5. Sorry, no, I is going to be 0, x is going to be 5. We're going to print from 5 to 25, but we're going to skip 15. What is this program? Anyway, let's just send it, see if it works. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then it stops. Did I use the wrong bytecode instruction, perhaps, because there was multiple returns? No, I mean, the bytecode seems okay. Let me see. Get up the bytecode instructions. Sorry for the flashbang. Can I make Wikipedia dark mode? Ugh. Appearance dark. Oh, God, there we go. All right. What is the difference between ret and return? Return. return void from a method. Okay. Ret. Continue execution from address taken from a local variable. Yeah, so like ret is for jumping around, whereas return is for functions. Am I stupid? Well, I is less than 20, call foo. But if x is 10, return, so we don't do the print. Oh, I don't think I compiled it after I changed it to 20. I think that was the problem. Yeah. Okay, I've got the stupid. And look, we skipped 15, so the return worked. We're not done yet, but we're so very close. So there is one final thing we need to check for in our program, and that is that every branch of a function returns if it's supposed to. Because currently we compile this absolutely fine with no diagnostics. But if we look at what we just emitted, it can't be decompiled, and if I try and run it, it's going to say something like empty stack, or method, yeah, the opposite. We've ended up with too much on the stack. Because we didn't check that there was ever a return. But thankfully, this is really easy. Like, it's one of those things that just like feels like a really complicated problem. But then you break it down, and it's actually really easy. Because we basically need to, for all of the possible branches in a program, figure out if it returns. So if you have a if or an if else, you need to make sure that both branches return, or it'll make sense as I do it. I feel like I'm not explaining it very well. So this is going to be done at the type checker, because there we're going to know if, or do we do it at the type checker? Because it might be possible to do it at the parser. Let's try it in the parser, because I feel like our type checker is pretty complicated. So let's say private bool, or boolean, all branches return. So what does this take? Well, let's figure out how we're going to call it. So if we're parsing a function here, we parse the body. So let's say if return type is not null. So we don't care what the type is. The type checker is going to figure that out. We just know that we have a return type. We need to say if all branches return, and we pass in the body. There we go. We want to say if not all branches return, report diagnostic, not all branches return. And I think the best we can do is just highlight the identifier. So let me add this. Yeah, we'll call it identifier. And let's say just not all branches return a value. And let's just pass a span, actually. No sense boxing it. And we just pass the identifier span. And then let's add that. So this is our signature. How do we determine that all branches return? Let's break it into different statements, different statement kinds. Let's say by default, they don't. Okay? Nothing returns. Except for return statement. Yield. I'm looking for yield. No, I'm not. Case oh, because of this stupid thing. Okay. Okay. Are we done? No. Because you could have something like a block, and inside the block you return. And in fact, yeah, most statements coming in this at first are going to be blocks. If we go back to where we actually pass it in, like we're going to parse a block statement, and then we're immediately going to say switch default false. So we need to handle block statements. And actually, we don't want to ignore this one. So how do we know if a block statement returns? Well, if the last statement in a block statement returns, then the block statement returns. So we just say block statement. So let's say get statements. Let's get the statements. If statements is empty, return yield false. Else yield statements last, or get last. Does it return? Do all branches of this return? Because this could be any statement. There we go. We did blocks. Then it's what if we have an if? Well, if there is an if, it will only return if both the if body and the else body return. If it's just an if by itself, we might have to do something like compile time checking the constant of the condition to see if it's always true or false. I don't want to deal with that now. So we just say if statement else body is null, yield false. And I'll just say to do can do compile time constant checking on the condition, but not right now. Else we just need to yield all branches return on the if statement body, and all branches return on the if statement else body. And we could do the same thing for whiles as well. If the condition is always true and the all branches return inside the while, then we always return. But currently I don't want to do any compile time checking, so for the purposes of this, while loops will never return. I think that is it. So if I run this, did I already fix this? I did. So if I break this again, we should now get a diagnostic. Not all branches return a value at span offset 3, which is here. Yeah, length 3. So it highlights this, well, it would highlight this function. If I say, if A equals B, I don't know why, but let's say return 2 times A. This is also going to fail, because not all branches return. But if I then said else return A plus B, both, oops, that's not what I wanted to do, yeah. Both branches do return, so this should pass. And it does. And if I check the emitted bytecode, it's done something clever. But it compiled, and it compiled to something different, and it still works. See? Because, you know, what I've done is functionally the same, logic-wise. And if I instead got rid of the else, but had this, like, you know, that was kind of a redundant else. If I had this flow, yeah, it still compiles. It probably compiled to the same underlying bytecode. Yeah, it does this still. But it works. So that's cool. Let's just get rid of that because that's stupid. So I think we're done. I think we're done with functions for now. Until we have compile time constants, we never have to touch that code again. Yeah. And we did it in a way that means that, like, types, you can now extend types, and that will then mean they work for variables and for function arguments and returns. So I think maybe next time we'll actually try and do arrays, because our arrays will be really easy to do now, Because first of all, they're supported natively inside the bytecode, so I don't have to do anything special like, you know, pointer offsets. It will just be mostly introducing syntax for the most part. Yeah, so we can do that. Yeah, it's really shaping up. And now we could probably do, yeah, once we add arrays, we can get away with this like sort of like pseudo scripting language-esque, and we can do something like fun main args, you know, and then, you know, that will compile to the main function of the bytecode, and then we are basically away from being a scripting language. Yeah. What else could we do next? Oh, and actually a big one is going to be custom types. So I don't really know how I'm going to handle user-defined types properly yet. Obviously we're going to have classes because this is a JVM language. It would be silly to not have classes. I know I want to have discriminated unions like Rust, but also I'm thinking it might be nice to have structs in quotes, because they're not really going to be structs like in C, but I think it would be nice to have them sort of behave like structs, in that they don't have any methods, they don't have any like associated behavior, and in fact we could probably do them. Okay, if you've enjoyed this video so far and you just came here to see me do functions, you can stop watching now because I'm just going to be like rambling. Yeah, I'm just going to keep rambling about types now. So if you've enjoyed it this far and you've made it this far, it's probably a long one today, but if you've made it this far, you probably don't mind that. So thank you again for watching, and thank you for coming along with me making Jura. Yeah, leave a comment, leave a like, let me know what you like, what you didn't like, all that good stuff, and I'll see you in the next one. But if you're sticking around because you want to hear me rant about structs in Java, you're a real one. So here's what I'm thinking. Let's hypothetical syntax this. If I was to say struct vector 2D, right? This is going to have an x, which is an int, and a y that's an int, right? That's it. No data. Sorry, not no data. No methods with my data. No functions with my data. There will be no like methods in this, but there can be like maybe like static things. So, you know, maybe it's nice to say like, you know, int, or like fun mag int, but we'll get to that when we get to that. Because what I'm thinking, okay, finally getting to what I'm thinking. If we decide to compile this as a class that is like final, for example, I don't know how fancy Java the JVM gets. I know they're working on stuff like this. Sorry, I'm sitting in the dark again. Let me just do that. I know they're working on something like this with records, but I don't know where it is yet. And also, I think they've shot themselves in the foot with records, because you can't treat them like value types properly. So I'm going to have a language construct which is a struct in Jura. So if I have a function like, sorry, I'm really rambling now. If I have a function like add v2, and it takes in v1 vector 2d, v2 vector 2d. If these were, and it returns a vector 2d, sure. If these were classes, what Java would do is allocate two, or you'd have to allocate two vectors on the heap, take the pointers to them all internally, and it passes the pointers to those heap allocated objects to this method, which then when you access v1 and v2, you have to then load them off the heap, and then you have to garbage collect them later on. But it would be nice if these were stack allocated, but you can't stack allocate objects in Java, as far as I know, at least not yet. I know they're working on something like that with Valhalla. But we don't have to compile them as classes because there's no methods. If I make the decision that there are no methods on vectors, or sorry, on structs, of which a vector2d would be a struct, I don't have to compile it like this. I can compile it like v1x int, v2x int, sorry, v1y int. Yeah, you see where I'm going? And then you would have v2x int, v2y int. And you could allocate this all on the stack. You don't have to mess with the heap at all. And then with returns, what you can do, I don't quite know how possible this is going to be to do like a multiple returns, but you could probably compile this in a way where, I don't know if arrays are allocated on the stack or not, or if you could even return arrays allocated on the stack. But like you could conceivably have like some construct here which says how to return it. No, you don't have to do that. You could instead make it void when you compile it, and you'd have like return v x int and return vy int. And so in here you could do like return vector2d x is v1 x plus v2 x. Good lord. Yeah, it doesn't know what I'm doing now. Y is v2 x plus v2 y v1 y. Yeah? So there would be some desugaring that happens in the compiler at the lowering step, which is why we have this step, that would take this, it would see, oh, I'm returning a struct, and I've mangled the function signature to all hell. So instead, all this is going to say is return vx equals v1x plus v2x, and then return vy equals v1y, something like that. Now, this doesn't work yet, so this is why I'm still thinking about this, because these get allocated on the stack in this function. Because in Java, this, if you pass in a primitive, it doesn't mutate the primitive. So like this is why in C you would do something like this with pointers, and then you would do something like that, I think. I don't think you can do that in Java bytecode quite like that, but there's got to be something you can do. Whether this like comes in as like a array, but then it's probably heap allocated. I don't know. You could probably get most of the way to like value types like this. Anyway, that is my rant, and I haven't quite figured this out properly, but that's something I would really like for Jura to be able to do. Mostly just to flex on Java, but also because I think it's a useful construct to be able to have value types that don't allocate on the heap. Because like when you have massive Java programs, like enterprise Java programs, and you have like hundreds of these objects coming into memory being allocated on the heap, you do have to be careful. You can't just be like, oh, it's a garbage collected language, who cares? Like you're gonna blow up your heap eventually. And if you can be smarter and use a value type when you don't need any associated data, like if you do just genuinely have some holder of data, if you can have that all on the stack, it's perfect because there's no garbage collection. It just deallocates when you leave the method that called it. Anyway, thank you again for watching. If you enjoyed my rant, please offer suggestions, because again, I haven't figured this all out yet. I know there's going to be a catch. I just haven't thought it through yet. But yeah, thank you for watching. It's been a long one, and I hope to see you in the next one. Bye bye.